good afternoon to you all. So last time I promised that we will study at last the spaces for which you can recover from the open spaces, lattice of open sets. And for that I need to observe something new related to the construction we had. So remember that we had decided that a point in a complete lattice L is a completely prime filter. But there's a simpler description of that. So you may think that I'm a complete crook and I've taken the complicated definition just to impress you. But the simpler definition has a problem, which is that it's easy to see what it is, but it's harder to work with because it will imply lots of negations and complementations, and I always get lost anyway when I use that second simpler definition. So let me try to make a drawing to tell you what the idea is. What is a completely prime filter? So here's L. Let me make experiments at drawing some subsets of L. What should be an upwards closed subset? Well, typically, I would like to draw an upwards closed subset this way, so everything above the line, meaning that if I take a point here, and if I go up, I remain there. So that's the usual way we represent upwards closed subsets. Now, what is a downwards closed subset? Well, typically it's something that I would represent this way, by taking everything below that. But the paradox that the drawing doesn't convey is that the complement of a... Is there an eraser, by the way? Yes. The complement of an upwards closed subset is downwards closed, and conversely. So the drawing is a bit misleading in that what's above this line is upwards closed, but a downwards closed subset can also have this kind of shape, which is kind of concave, whatever shape means. Okay, now, what can shape mean? Well, if I'm drawing it this way, this is a good way of saying that when you have 2 points here, their inf is still in it. So if you have this property, meaning that your upwards closed set is a filter, then there is some reason to draw a filter in a convex way this way, all right? And then you can see, the deadly phone from hell. And so in this case, you can imagine that there should be a dual property to being a filter for downwards closed subsets. And the dual property is an ideal, sometimes called an order ideal to distinguish it from ideals in rings. So an ideal is an ideal in a complete lattice. So the general definition is slightly different, but in a complete lattice I can define it this way. An ideal is a downwards closed set. So it's just like a filter, except I'm replacing upwards closed by downwards closed, non-empty, and the converse condition of the filter condition, which is that for an ideal I, okay, for every 2 elements x, y in I, the supremum is in I. So typically, an ideal, I should have written that inside it, is something which is downwards closed and empty, and if you take any 2 points, the supremum is still in it. So that's a kind of it is a dual property, in the sense that a filter is just an ideal in the lattice that you get by reversing the order. Now, we have talked about being prime for a filter. So a filter F, okay, F is prime. Remember that property, which is that for every 2 elements x, y in the lattice, if the supremum of the 2 elements is in F, then x is in F, or y is in F. Well, it turns out that if F is upwards closed prime set. Its complement, L minus F. So imagine F is upwards closed. I'm not yet assuming it's a filter. But L minus F is downwards closed because it's a complement of an upwards closed set. It may be empty in the case where F is the whole of L, but the interesting part is what becomes of that condition. It says for every two elements x, y in L, if x or y is not in the complement, we're going to do plenty of negations, double negations, and so on. So instead of doing that, I take directly the contrapositive of that. Okay? The contrapositive of that means if x is not in F and y is not in F, then x or y is not in F. That is, for every two elements of L minus F, x or y is in L minus F. So, up to the condition that it might be empty, this is exactly what I call an ideal. And graphically, that means that it would be sensible for a prime filter to draw it as follows. To say, well, a prime filter is just a filter whose complement is either empty or non-ideal. So we have that property for the complement. And in a sense, it should be both convex and concave. So a nice way of drawing that would be through a kind of straight separating line.
You say the complement of the filter, the complement of the union of the sets in the filter? Or?
No, the complement, the filter is a subset of L. So the complement is just all the elements of L which are not in the filter. When I say filter, it's not to say that the points here are filters. It's to say that that set is a filter.
Did you discuss this? Is there a connection to the notion of the directed set? So
absolutely. There's a direct connection. So a directed set in a coset, direct family, whatever, D, is, well, the usual definition is it's a non-empty set which has a property that for every two elements in D, there is a third element, maybe not different, in D, such that both x and y are below z. It turns out that fact, if D is, no, not if, that's not the right word. For every subset D included in a lattice L, a complete lattice is enough, but I have not defined what it is, and for every D which is downwards closed, then D is directed for downwards closed set, if and only if it is an ideal in the sense I said. The reason is that if it's an ideal, that is, you take any 2 points x and y, their supremum is again, so any two elements of D, their supremum is in D, because where I wrote it here, okay? So it says that for every two elements of D, their supremum is in D, so there is an element in D, the supremum, which is above x and y. And conversely, if you have this property, then if you take any two elements x and y of D, so any two elements x and y of D, there is an element in D, Z, which is above x and y, but you are in a lattice. In a lattice, the suprema of any pair of elements exists, so that thing exists, and this is the least upper bound of x and y. This is n upper bound, so z is above x or y. And because D is downwards closed, if z is in D, then that least upper bound is also in D because it's lower. So what we've proved is that if you have this property of being directed, so there is a z that satisfies all that, then actually you can take z to be equal to x or y, meaning that you have this property. So in that case, the two properties are equivalent. And in fact, the general definition of an ideal, not just in a complete lattice, but in any poset, is a directed downwards closed set. And it's fine that you ask the question, because I speak about ideals necessarily at some point later.
How does this work if we don't have a complete lattice, but just having, for example, CPOs or PCPOs or structures like these?
Yeah.
So which do not have necessarily one global supremum element, but there may be a family of these and have structures that go to them.
Okay. There are plenty of structures that are enrichments of posets. So DCPOs and for the others, I never know the name because people have different names to tell about them.
Okay.
And,
so that's not that standardized.
But directed sets exist in every poset.
Mm-hmm.
So you don't even need to have partial suprema or anything. Mm-hmm. Nothing needs to exist. A directed set is something that exists in every poset. The definition doesn't use any kind of suprema or family of least upper bounds or anything. And so in particular, downwards closed directed sets always exist. They're always meaningful. And in any poset. So there are ideals in any poset. The simpler ideals that you can find are something called principal ideals. A principal ideal is a set of elements below one point. That is downwards closed, clearly, and that is directed in that sense, okay? Because if you take any 2 points below x, there's a point above both of them, namely x, which is below x. And of course, you have other ideals, usually. Well, not just usually, all the time.
Very important one as well, the idea that PCOs, because you need suprema function spaces.
Yeah.
So if you take lattices and you typically have relation, but the suprema of relation are again relation and not necessarily function. So you can't use the framework for giving semantics for something like functional programming language directly. So
really? I have never encountered the problem. Okay. I have never encountered the problem. Maybe you could tell me what.
Well, the suprema is a relation, and you would have to prove that actually this element is again a function. You have too many elements as suprema in chains in this particular space. Then you have actually functions, elements that can be interpreted as functions.
You'll have to tell me more precisely what you mean later, I guess. Okay, so what I wanted to say here is that we already have a picture of what a prime filter is graphically, but there's even better for completely prime filters, and now we don't even need to read it graphically. So let me remove all that. And let me remind you what completely prime means. That means for every family UI of elements of L, if the supremum of the UIs is in the filter, so I started last time to call these points X, so I continue to use the same notation. So if the supremum is in X, then there is an element of that family which is already in X. And we started to look at the complements of filters, so it would be interesting to see what this means by taking the contrapositive. That is equivalent to saying that for every family, okay, if that is wrong, that is, if every element is in the complement of X, so now I'm taking any family of elements of the complement of X. So it's not L minus curly braces X, okay? It's L minus a subset of L, which is X. Then the supremum is also in the complement. So some people know about Scott-closed sets. It looks like it, except the condition for Scott closure is for every directed family of elements, and here it's for every family. Well, as a consequence, as a completely trivial consequence, just take what's the largest family of elements in L minus X that you can take? Reason like a mathematician. Take one of the two most obvious ones.
What is the question again?
Can you find the largest possible family of elements of L minus X? Yeah, L minus X. So L minus X is a family of elements of L minus X. What bothers you probably is that I have written the family of elements as an indexed family. So if you look at it as far as typing is concerned, this really is a map from some index set to L, or L minus X, and I'm now reasoning as if a family was just a subset. And mathematicians do the abuse of language, that the family is a subset, is a set, or it's a set indexed by some index set. And that's equivalent. If you really want that,
What does this mean? So it's a constant function that gives L minus X? Or
not at all, not at all. The usual trick.
What the notion of family is behind here.
Okay, for a mathematician, a family is ambiguously a set or a function from an index set I to elements UI. And if you type that into Coq, you'll soon realize that Coq complains that these are not the same kinds of objects. But for mathematicians, they're exactly the same things. And so I'm being pedantic now. So the point is that each time I was mentioning a family UI, I in I, what really interested me was in fact the set of UIs such that I is in I, and I'm using the indexing just so that the argument is more understandable to a human being. For whatever reason, a human being, unless he's really educated to think in those terms, prefers to work with indexing. But now, if I have any set S, I can consider it. It actually comes, okay, it's not bijective, it actually comes from an indexing, and the most trivial indexing possible, which is you let the indexing set be S itself, and you define U sub I as being I. You can self-index objects. And that is a standard trick in mathematics, which you learn normally at a young age. My teacher in class préparatoire, when he thought a result was obvious and didn't need further explanation, said, "You've probably learned that in kindergarten." So anyway, so I can consider L minus X as a family, and if you need an indexing, you do that trick. And so in particular, that family it's a family of elements of L minus X. It has a supremum, which is usually written this way, but this is what I said. Human beings tend to fail to understand that, and they tend to prefer saying complicated things like the supremum of all the elements U such that U is in L minus X. But really, for a human being, that's clearer, but for a machine, it's more complicated. More letters, more direction. So what I said is that this is in L minus X. So graphically, if you take a completely prime filter here, consider all the elements in the complement, all of them, they have a supremum, but that supremum is again in the complement. So that is the largest element of the complement. So I have a strange picture, which is that there's a distinguished element here. Let me call it U, such that all that is what is below U. So in particular, my point X is the complement in L of the downward closure of that element U, for U equal the supremum of the complement of X. So what I meant initially was, I said that points should be completely prime filters, so complicated things, second order things. But they're just elements of L after all, some elements of L. Do all elements of L qualify as points? Well, no, because what you get by taking the complement of the downward closure of U, that is whatever remains here, should be a filter. So, observation, note that U, that element U, we are going to reuse some adjectives, sorry for that, is a meet prime element, and that means that U is different from top, we'll prove that. And that for every two elements of the lattice, if the infimum of X and Y is below U, then one of the elements should already have been below U already. X is below U or Y is below U. Let me prove that, okay? What would happen if U were equal to top? The downward closure of U would be everything. The complement of that would be empty. But the complement should be a filter, which is not empty. Okay, so U can't be equal to top. Next thing, that property, if you take any two elements X and Y in L, do the contrapositive, that actually means X is in the downward closure of U. Okay, so if you take the contrapositive, that means if X is in the complement of the downward closure of U, so that, oh sorry, I'm reusing X. Ooh, bad. But I'm actually running out of letters.
A, B.
Well, yeah, if you wish. A, B. What? Oh, yes, yes. But then I tend to be strict on notation, and usually I have a kind of discipline that says these letters are for that kind of objects, and so on. Just like in good old Fortran, you know. And, no, nobody knows Fortran.
To be on the safe side, right?
I mean, I'm not talking about those fancy languages like Fortran 9x or even Fortran, the later versions, which I don't even know the names of. I'm talking about the real Fortran 66. Okay? By the way, does anybody understand the pun, God is integer unless declared otherwise? No, really nobody. Huh? It's a pun that detects the Fortran 66 users. The ones who laugh know Fortran 66. Okay, so the idea of the pun, sorry to spoil the thing. So God, oh, sorry, my pun was the wrong one. Okay, so I'm trying to, let's rewind and go back in time. The pun is, God is real unless declared integer. Because
Declared variables in Fortran are real variables.
not exactly. Variables in Fortran 66 have an implicit type. You don't need to declare them. As soon as you use them, the compiler knows that it has to create such a variable, and its type is determined by the first letter of its name. So I, J, K, M, N are integers. X, Y, Z, and in fact all the other letters are real. And unless you declare the variable, so you could declare integer God, and then God is integer, not real. Sorry, so it's actually planned to detect 466 users, but I botched it, so it's no worse. So anyway, let's come back to that situation. So that means, let's check that condition. It says for every B, A and B in L, if A and B is in down arrow U, then A or B is in down arrow U. And by taking contrapositives, that means if A is in the complement of down arrow U, that is, it's in X, and B is in X, similarly, then A and B is in X. And this is exactly what one of the conditions for a filter. Okay, so in fact, those specific elements we get here are very specific elements of L. They are meet prime elements. And because they are prime, some people, so there's a dual notion of join primes, where you say different from bottom, and there the condition is with supremum. In fact, I've used the notion meet prime, so that you don't confuse that with a prime filter. But in fact, people say prime when there's no risk of ambiguity between meet prime and join prime. So, because the first letter of meet prime is P, I'm going to say that those elements are called P. So the largest element of the complement of any completely prime filter is a meet prime element, which I'm going to call P. And conversely, any set you get as a complement of the downward closure of a meet prime element is a completely prime filter. I'll probably let you do the exercise. It's not hard. So in fact, conversely, for every meet prime P, the complement of the downward closure of P is a point. So instead of taking completely prime filters as points, I could have defined them as being the meet prime elements, and that would have, at least in principle, made the construction simpler, because this would have exhibited the set of points of the lattice as a subset of elements of the lattice. At this point, it would be nice to find a few examples. And because I'm a cheater, I'm going to rely on a cheat sheet. So I won't project anything, don't worry. That's not the reason why I'm using my laptop computer. What's it doing? I'm in the wrong configuration where so sometimes you wonder why people are doing computer science. Nothing really works the way you want. And of course the main window has disappeared. And so I do.
Same motivation that drove people into theology.
So Stefan is explaining something about theology, but I don't quite hear what you said. So let me find a few examples. Okay. Let's start with a simple example. Let's take the following lattice. Our set of 1, 2, 3. You can represent that as bottom element, which is empty, the empty set. This is one element set 1, this is 2, this is 3. Then you have the two element set 1, 2, which is above these two. The two element set 1, 3, which is above these two. The two element set 2, 3, which is above these two. So, okay. And this should have the shape of a, yes. it would be clearer if I do this way. This should have the shape of a cube. If you look at it, no, it's still not the right crossing. If not, this should be.
Should we change the 1, 3 and 2, 3 sets for it to really look
Yes, let's do that. I should have prepared that as a cube from the very start. So, okay, let me represent it as a cube, so that I'm safe. It doesn't have any consequence on the rest. So I start from this, and adding 1 goes this direction, adding 2 goes this direction, adding 3 goes in this direction. Now I can add 1 going this direction, or add 2 by going this direction. I can add 3 to this one going in this direction, or add 2 by going up. Then I could add 3 starting from here, and I get the top element. I could add 1 starting from here and get again the top element. Or I could add 3 starting from this and getting 1, 3. Or adding 1 to this one. Or I can add 2 to this one and get this one. So it's slightly default for the purpose of distinguishing these 2 elements. And what are the mid-prime elements of this lattice? Yeah, that's painful. I mean, the best way to do that is you program you code a little program, okay, that actually enumerates the elements, tests that condition, and produces you a list of the mid-prime elements. I guess that would be quicker to write a program, test it, and run it than just doing the exercise by hand. So let me give you the output of that virtual program. So I've invented virtual programming. That's the kind of thing in the spirit of Einstein. That might be called, I don't know, Gedankenprogrammierung.
But for Einstein, God didn't play with cubes.
No, God didn't play with cubes either, I guess. Especially three-dimensional cubes. Okay, so let me tell you the answer. The mid-primes are these elements. So that can't be the top element. The top is not mid-prime. And for example, 2 is not mid-prime because there are 2 elements A and B, for example, these 2, which have the property that if you take their if, this is here, it's below this element, but none of these elements is below this one. So if you take A this, B this, A and B is their intersection, so it's kind of the wrong.
Yeah, it's 2, 3.
It's 2, 3, yes. So 2 is their intersection. So A and B is below that, actually it's equal to that, but none of A and B are below this one. But you can check that, for example, this one is prime. So if you take A and B, well, any 2 elements A and B, and you imagine, so A and B is the intersection of A and B. If the intersection is included in that, that means it misses 3. Okay? If 3 is not in the intersection, that means that 3. So if 3 were in both A and B, it would be in the intersection. So if 3 is not in the intersection, then it can't be in A or it can't be in B. And that means that A must miss 3 or B must miss 3. But the only thing that you can do to miss 3, that is not to contain 3, is to be included in 1, 2. So one of the elements will be below 1, 2. So 1, 2 is prime, is mid-prime. That's no accident. And that's no accident because that is actually the set of open elements of 1, 2, 3 with a discrete topology. A discrete topology where every subset is open. So what I've done is I've produced the open set lattice of that very trivial space, and I've recovered the original space as its set of mid-prime elements. That should come as no surprise because for simple enough spaces, you can get back the original space by taking its points, the points of the lattice of open sets. So why am I doing all that? I'm doing all that because if you start from a topological space and look at what a meet prime element of the lattice of open set, so what is a meet prime of O of X? Okay, it's better defined through their complements. You haven't had enough of complements and negations, I hope. We're going to add a new instance. So let me say that U, it is meet prime if and only if letting C be its complement. So what is C? So the complement in the space X now. Let's translate these conditions in terms of complements. That means that U is not top, so U is not the whole space, meaning that its complement is not empty. So C is non-empty. And the other condition is if you take any two open subsets, I'm going to rewrite that. Let me use that as a scratch pad. It says for every AB open subsets, if A and B, which is A inter B, is below, that is included in the prime element A, then A is included in A or B is included, A is included in U or B is included in U. Let me use complements and a contraposition. That means for every C1, C2 closed, oh, I forgot to say what a closed set is. A closed set is the complement of an open set. Just that. I have to warn you if you've never heard of that before, there's absolutely no relation between closed sets and open sets apart the definition I just gave you. So in particular, never tell me, oh, it's open, so it can't be closed. No. You can be both open and closed. You can be neither open nor closed. Okay? For example, the empty set is both open and closed. The whole set is both open and closed. Because the open set is a complement of the whole set. So the empty set is a complement of an open set, so it's closed. But it's also open by definition, and so on. In your favorite spaces, like R cube, those are the only open and closed sets, okay? But there are spaces where you have more. So, let me say, for every C1, C2 closed, I mean that C1 should be taken as a complement of A, C2 should be taken as a complement of B. Now C should be taken as a complement of U. Okay? Now that means what is the intersection of two complements? The complement of C1 and C2. That's the complement of their union. Now a complement is included in complement if and only if you got the inclusion in the reverse direction. So that actually means if C is included in C1 union C2, then complement of C1 is included in complement of C, meaning C is included in C1, or C is included in C2. Now I have my final condition. So U is meet prime if and only if you take this complement in X, it's non-empty, and for any two closed sets, if C is included in C1 union C2, then C is included in C1 or C is included in C2. By definition, there's a new ingredient. That means definition. So I'm kind of overlapping proofs, arguments, and definitions. Definition C as a closed set is irreducible if and only if it's non-empty and satisfies this property. irreducible sets play a very important role in that theory. Another equivalent property is, instead of using complement C1 for A and C2 for B, let me just rename A and B U1, U2, they are open. And then use complementation. Okay, so an equivalent condition is for every two open sets, U1 and U2, if U1 is not included in U, that is, okay, if U1 is not included in U means you have U, but U1 must contain some point outside. That means that U1 intersects the complement of U, which is C. So that means that, no, I'm not doing the contrapositive. So if U1 is, so what I want to say is that the equivalent condition is if C intersects U1, which is a negation of the property, and C intersects U2, then you got the negation of that other property, which is that C must intersect both the intersection of U1 and U2. Of course, you know that it's not a property that usually holds of a subset. Okay? That's a typical error from students who say, oh, C intersects U1 and it intersects U2, so that's the definition, it intersects U1 into U2. But you know that's wrong. Okay? That's wrong unless C is irreducible. What do you have as irreducible elements? Well, I claim that for every x in X, so point in the usual sense, the closure of X, that is every set has a closure. That is, every set is contained in a smallest closed set that contains it. They are the smallest closed set that contains any fixed set. It's just the intersection of all the closed sets that contain it, because any intersection of closed sets is closed. So there's the closure of a single point. In the usual ambient space, so in general in Hausdorff spaces, the closure of a single point is just the single point. But it won't be the case in general topological spaces. And you can in fact check, have I told about the spatialization ordering? Yes. So you can check that this is exactly the downwards closure of the single point X. Always. Should I do the proof? It's maybe not obvious. So remember that X is below Y if and only if for every U open, I won't, just like in Fortran, U will always be open, so I won't write it. C will almost always be closed, and so on. So that means for every U, if X is in U, then Y is in U. Okay, so we can rewrite that in terms of closed sets. It's all Boolean algebra, really, what we are doing today. It says for every closed set, taking C as the complement of U, if X is not in C, then Y is not in C. Now take the contrapositive. That means if Y is in C, then X is in C. Okay? But in particular, if that holds for the closure of Y. Right? The closure of Y is closed and it contains Y. So if that holds for every set C, it must hold for the closure of Y. So in particular, X must be in the closure of Y. And conversely, if X is in the closure of Y, every closed set that contains Y must contain the intersection of these closed sets that contains Y. So C must contain the closure of Y. So X should be in C, because X is in the closure of Y, which is included in C. So that is actually an equivalence. Now the conclusion of that is that the closure of any element Y is a set of x's that satisfies this property and that satisfies this one. This is exactly the downwards closure of y. So the closure of a single point is very easy to describe in order theoretic terms, knowing that you have a specialization quasi-ordering. I claim that this is always an irreducible closed set. It's non-empty, right? And if it's included in the union of two closed sets, C1 union C2, that means that X in particular is in that set. So it's in the union of C1 union C2. So X must be in C1 or C2. If X is in C1, I claim that the whole downward closure of X must be in C1. Well, you can say so because you can realize that closed sets are always downwards closed with respect to the specialization quasi-ordering. Or you say the downward closure of X is a closure of X. So it's the smallest closed set containing X. And if X is in some closed set, that closed set must contain the smallest closed set containing X. So that is always irreducible. But in fact, we have already done that. It's just done in a different language. Remember last time we had said if I start from X, I start from a point X, and I have this map which goes to PT of O of X, which maps X to the set of open neighborhoods of X. What have we done today? Well, we have observed that this is a completely prime filter, but this must be equal to the complement of the downward closure in O of X of some mid prime element. And that mid prime element is just the closure of X. You have to verify that. So what I mean is that this is the whole lattice minus the downward closure in O of X. I'm writing the subscript to make clear in which set we are taking downward closures of a mid prime element. I've said that the mid prime elements of O of X are exactly the complements of irreducible closed sets. So here you take the complement in X of the closure of X, which is the downward closure of X in the specialization ordering of X. All of those of you who love negations and complementations rejoice. So this should bring fuel to my claims that completely prime filters are not that complicated after all. At least they dispense us with the need for having complements and negations everywhere. But anyway, check the time. I should almost finish. The point is that there is a bijection between that space and a space which I usually call the subrification, but which should really be called the standard subrification of X. And I'm using the notation S of X, but the standard notation is X exponent small s, and I've already used X hat in a different context, where instead of taking completely prime filters, I'm taking complements of mid prime elements. So the elements here, so I'm now mapping X not to that, but to this. So it's just a closure of X. And S of X, by definition, is a set of complements of mid prime elements of O of X. So that is a set of C closed, such that C is irreducible. In shorter parlance, it's the set of irreducible closed subsets. And what I've said is that the equivalent, that map eta we had earlier could be described in an equivalent way as a map from X to something called the subrification of X, which maps X to its closure or downwards closure in a space consisting of all irreducible closed subsets. And the only thing I have not described is the topology on S of X. that is a bijection. You have a topology here. I claim that in that situation there's a unique topology there which makes a bijection become a homomorphism. That's called transporting a topology along a bijection. And to do that, you just have to take here the sets of elements here, so the sets of irreducible closed subsets, which are mapped by that bijection to an open set here. Let's do that. So now remember our open sets here were sets I called O sub an element of the lattice. So that was an open set, U. And that was a set of points which were completely prime filters. F, completely prime filter, such that F contains U, such that U is in F. That was our open set. Now translate that to meet primes. Okay, so the completely prime filters are exactly the complements in O of X of downward closures in O of X of meet primes, and we see that the meet primes are, no, sorry, they are not all this form, but the meet primes have the property that they are exactly the complements of irreducible closed sets. Such that U belongs to that. U is in it, in short. What does it mean for U to be in it? So U is in OX minus downward closure, blah, blah, blah. I hope I'm not making any mistake. So again, machines do that easier than us. If and only if U is not in that downward closure, so U is not included in X minus C, in pictures. C, X minus C is the rest of that, and that means that U can't be inside the rest, so it must intersect C. That is equivalent to U inter C is non-empty. And that's the shape of the open set you want here. And these open sets are usually called diamond U. Diamond U is a set of closed, irreducible closed sets here, which meet U, which intersect U. And that is the topology we're taking on that subrification. So now, why have I done all that? So subrification is a set of all irreducible closed subsets with the topology of all the sets diamond U, U open in X, and because we've got exactly a bijection between the opens of the topology here and a set here, this is immediately topology, okay? I don't have to check anything. But if you want to check that, do that, please, and you realize that to check that these sets are closed under finite intersections, you need to check to use the fact that these elements C are irreducible. All right. So that is called the subrification of X, or standard subrification of X. And now I would like to show the following theorem. So first, another definition. Let me say that a space X is sober. The name was invented by Grothendieck, I think, and it allows for a host of puns. So there are famous papers like, I shouldn't drop names, but then there's Scott is not always sober. That's an actual title of the paper. The theorem proved in that paper is that the Scott topology on a DCPO may not be sober. The initials of the author are PJ. When Scott is weak at the top by AE, which means when the subspace topology is a set of maximal elements of a DCPO induced by the Scott topology coincides with a weak topology. Okay. So plenty of puns like that, and apparently Daniel Scott doesn't take any offense, which is fine.
He's old enough.
Oh no. I hope nobody has heard that. So X is sober if and only if. Remember that I said that this set is always irreducible closed? Well, sober, almost, not quite, means those are exactly the irreducible sets. You don't have any more. It's a bit more than that. X is sober if and only if every irreducible closed set is of the form closure or down arrow of some point, and the only thing where I lied is it's not for some point, it's for some unique point. This is just a trick. It's equivalent to saying that, or to say for some point and the space should be T0. That is, the specialization pre-ordering should be an ordering. Now, the theorem, it's just a proposition, not really a theorem. S of x, the sobrification, it would be a good idea to change things. S of x is sober, always. That looks obvious, right? You sobrify, it should become sober. That doesn't mean that you could do that without a proof. And again, that's a proof that's much easier. I'm claiming that, but Evelyn should take that as a kind of challenge. It's easier for a machine than for a human being. What I mean is that it's the kind of proof that's intimidating. You're here, you say, oh no, S of x is a space of reducible closed sets, it's incredibly complicated, what do I have to do for that? In the end, normally it's very simple, but it's just simple pushing. Don't try to get any intuition. So it's a kind of proof that is easier to find by simple pushing than by intuition. So, let C, curly C, to distinguish it from the ordinary C's which are closed in X, curly C should be closed in S of X. So it's a closed set whose elements are closed sets. Okay, so let C be irreducible closed in S of X. What I would like to show is that C, so it's a technique that I use with my students in the sometimes vain hope of telling them not to mix assumptions and conclusions. And this is an attempt to tell them, okay, I put here what I know and what I would like to have. But please note that they are not located on the same part of the whiteboard. And so what I would like to show is that C is a downward closure in S of X of some closed set. C for C close, an irreducible closed set of X. So for some C. First problem I have is I don't really know until now what the specialization ordering of S of X is. So let me compute that. Lemma. The specialization pre-ordering of S of X is, you have a guess, and except those who know, usual trick so that nobody can reply really. But it's widely applied in elementary classes. Inclusion, exactly. But you did know, right?
Yes.
Proof? Well, take two elements of C of X, of S of X. C1 is below C2 in that specialization preordering, by definition, if and only if every open set that contains this contains that. But we know the shape of open sets. They are all of the form diamond U. So that's not legal to write that usually, but you know that every open set is of the form diamond U. Okay, so I can say for every diamond U. I should say for every U. Okay? If C1 is in diamond U, then C2 is in diamond U. That's the definition. Okay? That means for every U which is open in X, C1 intersects U implies C2 intersects U. Let us take a special open set. For example, the complement of C2. You know military randomness? So military randomness is not at all random. It's an old joke that military is an adjective that negates the substantive, it's a group too. And so I'm using military randomness here. So for U equals the complement of C2 in X, that can't be true, right? C2 never intersects its complement. So that can't be true. So that means that C1 intersects the complement of C2. What does it mean for C1 to intersect? No, it's is empty. Yes, is empty. It's a negation of that. So C1 is disjoint from the complement of X minus C2. So C1, okay, in pictures, take C2, the complement, and C1 is here, but it can't actually intersect C. Sorry, it's not here. So C1 cannot have any point outside of C2. So C1 must be entirely there. That means C1 is included in C2. Conversely, if C1 is included in C2, take any open sets that intersect C1. So you find a point in C1 and also in U. That point is in C2 and also in U. So that is an equivalence. Yes?
Is it true that an irreducible is you can't find two disjoint non-empty open sets for the induced topology?
Two disjoint non-empty open sets, which?
For the induced topology and the irreducible closed set.
No, you can.
Okay, I'll check that.
No, there are plenty of properties that look like. And this one, so how many negations did you have already? So you said you want a closed set such that if you take any two open subsets in the induced topology,
If there are disjoints, then
yeah.
one of the two has to be empty.
Okay, if they are disjoint, okay, so you can't, if they are non-empty, they can't be disjoint. That's an incredibly strange property. That means that the ordering between non-empty open sets must be a total ordering, hence a chain. And yeah, I guess that means your space is some kind of chain itself as well.
Okay, I wrote it down.
Okay. So now we know that this downward closure of C should be all the irreducible closed sets included in C. So how do you find C? The non-curly version. And you know that C, curly C, should be everything that's included in C, including C. Well, that means that C should be the largest element of the curly C. In particular, that largest element should exist. Now, let me, sorry, it kind of overflows. Let me write that curly C is irreducible closed. Let me also say something important. Remember that we know all the open subsets. So we know all the closed subsets. So C being closed must be the complement in S of X of something which is diamond U for some open set U. Well, some students nowadays have been trained to do exercises. You know, modern forms of exercises in high school today are the form where you have a document, you have to read it, and you're given a table of constants, and then you have to answer questions. And a lot of students actually answer questions by realizing that most of the answers appear already in the table of constants and draw some number at random. I claim that this strategy is the right one here, is one which gives good results here. So that gives us an open set in X. We're looking for a closed set in X. Hint, hint. So let C be the complement in X of U. All right. What you know that it means, we've used the fact that it's closed, but it's irreducible. So what does this mean? Earlier, I had said, but I've erased it. I'm going to use a more practical definition for the purpose at time, that C is irreducible if and only if C is non-empty, and for every two open sets, if C intersects U1 and C intersects U2, sorry, different from empty each time, then C intersects their intersection. So if we write this definition here, that means we know that round C being irreducible means that for every two open sets of S of X, they are all of the form diamond U1, diamond U2. If C round meets diamond U1 and C round meets diamond U2, then C round meets the intersection of diamond U2 and diamond U1 and diamond U2. Okay. Now, what are these intersections? C round inter diamond U1. So C round is this. That is non-empty. If and only if, again, Boolean algebra, the complement of diamond U meets diamond U1. So again, my favorite picture. Diamond U1. Diamond U has a complement, so I should actually draw diamond U. Diamond U, so the complement of diamond U, everything outside it here, should meet diamond U1, meaning that diamond U1 can't be included here. There must be something outside in diamond U1. So that means that diamond U is not included in diamond U1. So that means that there's a closed set, C1, which intersects U and doesn't intersect U1. And in particular, if you take a point in that intersection, that point can't be in that intersection. Probably I'm doing things a bit in a complicated way here. Yeah, so that means that normally that should mean that U is just not included in U1. So does this mean that, can we check that? Is U not included in U1? Well, if every point in U were in U1, if for every x in U, x is in U1, then I can take C1 to be the downward closure of x. So C1 intersects U at x. And by assumption, C1, which is that, can't intersect U1. So in particular, x is not in U1. So indeed, that condition implies that U is not included in U1. And conversely, it's easier to show that if diamond U is included in diamond U1, then U is included in U1. Okay? So if diamond U is included in diamond U1, then for every element of U, the downward closure of X is a closed set which intersects U, so it's in diamond U. Hence it's in diamond U1, meaning that every element below X, in particular X, intersects, meaning that downward closure of X intersects U1, but U1 is upwards closed. Okay? So if downward closure of X, which is that, intersects U1, that means there's a point in here. That point is below X, but every point above Y is in U1 because open sets are upwards closed. Did I say that already, that upwards closed sets? Oh, open sets are upwards closed? Yeah, I think so. So in particular, that means that X is in U1. So we've shown that U is included in U1. Okay, so now I thought it would be shorter as a proof, by the way, which explains why I'm lacking some space. So, that C round is irreducible means that for every open set, so let me say U1, U2 from X, I'm generating diamond U1, diamond U2, if this condition holds, and we've seen that it is equivalent to U is not included in U1. And similarly, U is not included in U2, then it's a bit more complicated. Diamonds do not commute with intersections. They commute with all unions, but not, they do commute with intersections because we're in a set of reducible closed sets. So, observation, diamond U1, and this is what I should have done to show that it's topology. Diamond U1 inter diamond U2 is a set of irreducible closed sets such that C is in diamond U1, that is such that C inter U1 is non-empty, and C inter U2 is non-empty. But because it's irreducible, that actually implies, so it's included now, that every C that has these properties will also intersect U1 inter U2. So this is one of the equivalent definitions of irreducibility. And conversely, if C meets U1 inter U2, certainly it meets both U1 and U2. So that is an equality, and that is by definition diamond of U1 inter U2. So the last condition we had is of the form C inter diamond of something different from 0. So that means U is not included in U1 inter U2. Let's use contraposition. That means that if you take any two open sets, if U is included in the excuse me?
So you wanted to contrapropose, so
Yes.
U1 intersect U2.
But I've not yet contraposed. I'm doing that now. So if U is included in U1 inter U2, then U is included in U1 or U is included in U2. Good. Let me phrase that in terms of C now. And taking complements of these open sets. For every C1, C2 closed, if, now I'm taking complements, so if the complement of C is included in the complement of C1 into the complement of C2, move everything back around, that means if C1 union C2 is included in C, it's a bit strange. I hope I haven't made any mistake.
I'm wondering about the second line.
Second line here?
It sounds obvious for any set.
Yes, that's the problem I have.
Yeah.
Yeah, I must have made a mistake somewhere. So let me see where. C inter diamond U1. Okay, C is complement of diamond U. Yes. Okay, complement of diamond U. Okay, meets the diamond of U1. So there's an element in diamond U1 which is not in diamond U, so diamond U1 is not included. Oh, yeah, the mistake is already here. It should be diamond U1 is not included in diamond U. Okay, that means there's an element in W1 which is not in diamond U. So diamond U1 is not included in diamond U. I'm sorry. I told you it was easier for a machine than for a human being.
So you're not a machine.
I'm not a machine. That's another nice piece of news. Huh?
Nice corollary.
Okay, then we do the normal datation. Okay, and so that means that it should be U1 not included in U, U2 not included in U. Then I can't really do just a patch. Then U1 inter U2 is not included in U. Now by contraposition, that means that if U1 inter U2 is included in U, then either U1 or U2 is included in U, and that's much better. That actually says that U is a mid-prime element. Meaning that all that was useless. I knew it already, because that's the way I got all these things. Okay? So I'm actually recovering the fact that I'm considering mid-prime elements of O of X, as I started to say initially. So now taking complements, that means for every C1, C2, if this is all complements, and you take the so the complement of that is included. The complement of this other thing, meaning if C is included in C1 union C2, then C is included in C1 or C is included in C2. Aha. Doesn't it ring a bell? That's half of the condition for C being irreducible. The other one was C is non-empty. Why should C be non-empty? If C were empty, then U would be the whole of X. If U is the whole of X, then diamond U is the whole of S of X. Okay? Because diamond X, okay, is a set of irreducible closed sets that meet X. That is, those that are non-empty, they are all non-empty. So diamond X is the whole space. So S of X minus diamond X is empty. That is not possible because C round being irreducible is non-empty. So we have this, we have that C is non-empty, hence C is an irreducible closed subset of X, that is, it's an element of S of X. Okay? Yeah, part of this, which we want to prove, is that C is an element of S of X such that we can get all the others. Okay? So we should check that C is in round C. Well, how you do that? Well, you have to show that C, which is X minus U, is in C round minus, is in C round, which is that complement. Okay. If you rewrite this, that means that X minus U is not there, meaning that the intersection of X minus U with U is not non-empty. That's true. U never intersects its complement. Okay, so C is indeed in C round. And now we have to show that every element in C round is included in C. So for every C prime in C round, well, by definition, C prime is not in diamond U. That means that the intersection with U is empty. But U is a complement of C. And so that means that C prime is included in the complement of C. It doesn't meet U because it's contained in the rest. So that means that C prime is below C. So what have we shown? We have found an element C in C round, such that every element in C round is below C. So this actually means C round is included in the down closure of C Sx of that element C. But then we've shown that C is in C round, and because the down closure of C is the closure of C in S of X, and C round is a closed set that contains it, it contains the smallest one, which is the closure. So that is included in C round. So all these things are equal, and we're at last finished.
And what about unicity?
Unicity. Inclusion is not just a pre-ordering, it's an ordering. So the space is T0. Now if you want to do it explicitly, imagine that C round were equal to downward closure of both C and C prime. Okay? If downward closure of C is equal to downward closure of C prime in S of X, then C is that. Okay? C is below itself. So C is in that. So C is below C prime. That is, it's included. Now C prime, symmetrically, is in there. So it's in there. So C prime is included in C. That means that C equals C prime. So there could be only one. Yes?
Yeah, I'm coming back to what I was saying earlier. I think I didn't explain well, but it's exactly what is written here.
Yes.
So, diamond U1 intersection diamond U2, and the right you have the characteristic implication of the irreducible close.
Yes.
And if you take the contrapposite from down to top,
What do you mean?
If the
implication is this implies that?
Yes. So on the bottom line, if the intersection is empty, then on the top line, one of the two must be empty.
Yes.
And so I think it's that in the induced topology, you can't find two disjoint non-empty open sets.
Okay, let me see what this would mean, what you say. It would be that for every U1, U2 open, if C intersects U1 inter U2 is empty, then C inter U1 is empty, or C inter U2 is empty. So, indeed, that means that for every two, let me call them V1, V2, meaning open subsets in the subspace topology, that is C inter U1, I'm calling that V1, C union, and then inter, so it's not distribution, it's always, both of these are intersections, okay? So, but it rewrites as V1 inter V2, where V1 is C inter U1, V2 is C inter U2, and every V1, V2 open in the subspace topology can be written this way. So we are saying that if they have empty intersection, then V1 is empty or V2 is empty indeed. Yes, in fact, yes. Sorry. Yeah, it's a well-known. Yeah, I should have. Oh, all right. Okay. The spaces that have this property. So usually it's said in the contrapositive form again. So spaces in which, if you take any two non-empty open sets, have non-empty intersection, they are called the hyper-connected spaces. There's something called connectivity. Okay, so a space is connected if and only if it has no non-trivial open-closed subset. So the only ones are empty in the whole space, and that in particular means that. So every space that has this property is connected. It's a very strange property. Okay, it says that you take any two open sets, non-empty, whatever they are, they meet. Okay, yeah, and you are right, Valentin. A sober space is a space in which every closed subspace is hyperconnected.
And it's a characterization.
Yes. No, sorry, I said something stupid. That is a definition of an irreducible closed set. So it says the irreducible closed sets are the non-empty closed subspaces which are hyperconnected. And sober means the only non-empty hyperconnected closed subspaces are closures of a single point, of a unique point. I guess we should stop there, although we haven't done much really. But we have the important property that every subverification is sober, which seems so stupid it doesn't deserve something. But perhaps later we'll see that S is actually functor, and it's the functor part of a monad, which is a monad associated to the adjunction I've not talked about, which is O adjoined to PT. And what I've shown here is essentially that S, if you subverify a second time, that is, if you take S of X, you get something that is isomorphic to S of X. We've proved essentially half of it, which means that that monad has a very strong property. It's an idempotent monad. So I could say that in category theory. That would probably not be that useful. That means that S of X, as we have seen earlier, S of X is almost PT of O of X. We've seen last time that it kept the same lattice of open sets, but it added some points. What I claim is that S of X, then, it's another description of the same thing, but a very practical one. S of X is a construction that adds new points to X, keeps the same open sets, but if you reapply S of X to complete that, you don't add anything. It's really what you would like a completion to be. Once you complete the space, you get a complete space. That seems so obvious. So if you take the Cauchy completion of a metric space, you get a complete metric space. And if you take its own, the Cauchy completion of a Cauchy completion, you don't get anything more. Great. If you take the ideal completion of a DCPO, I've mentioned ideals earlier. There's also a notion of ideal completion, that is, you can embed every space by mapping X again to down arrow of X. Down arrow of X is an ideal, and then you can embed any DCPO in the space of its ideals ordered by inclusion. That is a completion, but that one is not idempotent. If you complete a second time, usually it adds further points. And in fact, it never stops. There's no point at which the construction stops, even transfinitely. So no, actually, that's a kind of miracle to have an idempotent monad. That actually happens rarely.